Mooring, Ramesh Pereira, Anand Pala, and Abir Al-Taba. Thank you very much.
Okay, hello everybody, I'm Abbas. For those who don't know me, I've been part of the Future Roads for the past 3 years. Right now I've joined University of East London working on similar topics. So if you were here yesterday on the workshop that we did, we talked about the durability of, we talked about actually how we can get the geopolymers onto the roads from lab to the field. And then at the end, one of the main points that was risen was the durability and the bottleneck that it has. So to get that and to get the reliability that we want from the materials and to use that, we need to understand how we can check the durability of geopolymers. But when we're talking about geopolymers and durability, the thing is that it's all about chemistry. So we need to understand the difference in chemistry between a Portland cement and a geopolymer. So Portland cement, you have a clinker, you mix it with water, and it gives you a tiny molecule of this CSH. And the water, most of the time, most of the water stays inbound with the system, and some of it evaporates. But when you look at the geopolymer, the precursor is silica and aluminum silicate, and you mix that with a silicate solution. And that will dissolve the material, that's the solution, and then you will have another stage that called polycondensation, which means that the aluminum and silicate will react with each other and produce a polymer. Hence the word geopolymer comes from this, because that's a polymer and this is a hydrate. The water inside the geopolymer will leave the system, and that's proven by the calorimeter test that you do, that the water doesn't take part in any of the reactions. It's just a matter of transport. So the whole idea of this review paper was to see how we can check the durability of geopolymers, and can we use the ones that is available for concrete for geopolymers. So in the first step, we see that talking about durability, talking about chemistry, we have a huge difference in the beginning. So the two major defects that I'm going to speak about is carbonation, and it's obviously when the carbon in the atmosphere tries to eat the calcium in your cement and concrete, and then it reaches the rebars, and rusting will occur. And the other one that we will look into is chloride ingress. So when you desalt the pavements, or it's close to sea salt water, diffusion happens, and that is that chloride from high saturation moves to the inside of your concrete, which has no chloride, and then a similar thing will happen, that the rebars will lose their protective barrier and they will start to crack. So just to have the definition of what we are trying to look into. So the normal thing for the carbonation when you're working with concrete is that you put it in a chamber, your specimen 3 to 5%, few weeks, and then you run the test and you use your available models to see how they work with the actual data in the field, and you have a sense of a value of the carbonation and how much the carbon has penetrated into the depth. But if we want to use the same parameters for geopolymers, then the case will leave about 3 to 10% variation or overestimation of the geopolymer. And that is mainly because geopolymers are not made out of that much calcium that the normal concrete is. So then the pH level will drop more dramatically when it's introduced with the atmosphere, the CO2. And that will lead to overestimation of the material. So just to make things more complicated, if you use different types of clays, so if it's just with the metakaolin or it's slag and fly ash, it will give you different readings in terms of the carbonation. So not only on geopolymer, but on different compositions, even you use it, you will have different results. So there's a lot of misreadings happening, and 3 to 10% variation is times variation is quite a lot. So just going to the next test, which is the chloride test. So the idea is that you soak your material between two different salts, and you pass 60 volt current through that, and from there you will understand how much electric charge passes through the material, and from there you will understand how good your material is against the chloride ingress. So the less electric charge passes, the better the material is. So why can't we use this for the geopolymer? Because of a few things. The first thing is that geopolymers, at some point, they have soluble pores, alkali soluble pores, and they can be conductive. So that means when you try to pass a current through them using 60 volt, the sodium and potassium materials, ions used, they will also pass. Because the thing about this test is when you're trying to understand the chloride ingress, you don't count the chloride ions passing through. You look at the total charge passing through your material, and that makes things a bit complicated. So this high ionic conductivity that geopolymer has, and when you add 60 volt, it will heat up the material, and that will also excite the atoms inside your geopolymers, and that will turn your geopolymer into a disco. So the materials, the sodiums, the potassiums, and everything inside will start moving, and you will have more voltage passing, and that is not true. That doesn't show that this material is prone to ingress. That's just the natural behavior of geopolymer is. And again, just to make things more complicated than they are, because with geopolymers, I guess it is like that. When we are designing for a geopolymer, the whole idea is to make it a neutral material. So for any aluminium ion, you need a sodium to balance the whole charge of the material. That's why we design for Na over aluminium to 1, so we can have a stable material. But the issue is that no matter how hard we try, we can't get close to the theory, and you will have excess liquid or activators lying around, and when they are drying and they get in touch with the humidity in the atmosphere, they will show conductivity. So this is another reason that the current tests that we use for concrete cannot be used that much for geopolymers. And you can also use this if you want to see how reactive or how well your geopolymer is designed. You can run the test, and then if you have lower conductivity, that means that the lower you have less ions, sodium or potassium ions lying around, and that makes your geopolymer more condensed, and everything, all the reaction has been complete. So by that, you can see that your geopolymer is well cured or not. So at the end of the day, you will be approving a material wrongly, or you will reject a very good material because of this overestimation. So you don't know which is correct, which is wrong. 3 to 10 times extra for the carbonation, that's quite a lot. And this is why until like 1 or 2 years ago, Australian standard was the only standard that I could find that was working directly with geopolymers. And from there, they have proposed that instead of using 3 to 5%, you need to cap that to 1%, and instead of several weeks, only 72 hours. For the chloride ingress, you turn down the lights, you shut down the disco, and everything will work perfectly. So you reduce that to 10 volts, and that will, instead of 6 hours of being soaked in a solution, you do it for 60 minutes. So that will cure everything much better, and maybe show better resemblance to the actual field. And when you have critical application, they are suggesting that you do electromechanical verification. So at the end of the day, this open question, this gap in any literature review is apparent, that what should we do? Should we stick with the material and use the same testing results as we have in concrete? Or should we just change them a little bit and use it for geopolymer, or try to produce something from scratch for geopolymer, but then in the meantime, keep working with what we have? And I guess that's it. That's the end of the presentation. Any questions? Thank you.